Welcome to The Explainer, where we break down complex topics. Today we're talking about something millions of us use daily without giving it a second thought, the hydraulic elevator.
You step in, you press a button, and you trust it. But do you ever stop and think about the invisible battle that's happening just a few feet away from you? Well, thanks to some fantastic insights from the experts at Novenpuya Elevator, we're going to pull back the curtain on the incredible engineering that keeps a single metal pillar from failing under immense pressure. Okay, let's dive right into it.
All right, first up, the elevator's unseen muscle. We're talking about the hydraulic jack, which is basically the elevator's backbone. You see, in a hydraulic elevator, the absolute hero of our story is this thing called the jack. It's a single, super powerful piston, and its one job is to lift and hold thousands upon thousands of pounds.
So you can really think of this jack as the elevator's spinal column. It's the primary structure bearing all that weight. And because of that, you can probably guess that designing it correctly is, well, it's not just important, it's absolutely critical. I mean, any tiny miscalculation here, we're talking about the potential for catastrophic failure. So yeah, the stakes are pretty high. So, what's the first big challenge? It's the main force, pressure. This is all about understanding that upward push. Now, the most obvious hurdle for the jack is just overcoming what's called static pressure. That's the raw force needed to get the car moving up. But here's the catch. That pressure is not a constant number. Static pressure is basically the force the hydraulic fluid is putting on everything when it's either standing still or just moving along at a steady speed, and it's directly tied to how much weight is in the car. So to make sure this system is rock solid and can handle anything you throw at it, engineers have to plan for the absolute extremes, and that means they have to calculate the pressure at two very different ends of the spectrum. So you've got these two scenarios. On one hand, you have P static max. That's the maximum pressure. Think about it, a car jam-packed with people moving upwards. The pump is working its absolute hardest. The entire system, every single component, is designed around this number. But then you have the other side of the coin, P static min. This is an empty car moving down, where gravity is doing most of the work. And you might think, who cares about that? But it's actually just as crucial, because you need to make sure the elevator stays smooth and under control, even with the lightest possible load.
Okay, so lifting is one thing, and honestly, if that were the only challenge, the engineering would be, well, a lot simpler. But the real danger, the kind of hidden enemy in all this, comes from forces that don't push up or down, but from the side. They're trying to bend the jack. And that's where things get really interesting.
So where do these side forces even come from? Well, they're everywhere. Think about it. Eccentric loading? That's just a fancy way of saying you and your friends are all standing on one side of the elevator. Then you've got tiny, almost invisible bumps in the guide rails, or maybe a microscopic misalignment when it was installed. Even sudden stops can do it. All of these seemingly minor things add up, and they create what's called a bending moment. Basically, a sideways push that is constantly trying to destabilize that long, thin jack.
And if those side forces get strong enough, if that sideways push becomes too much, you get this, buckling. It's when the jack suddenly bows out and just collapses. This isn't just a problem, it's the primary way these things can fail, and it's what engineers have to prevent absolutely at all costs.
So how on earth do you engineer against something like that? How do you win this unseen battle? Well, you definitely don't guess. Engineers use a super precise process called buckling analysis. It's the math that guarantees the jack's stability, making sure it can handle both the immense vertical load and those sneaky side forces at the exact same time.
And here's how that analysis works. It's a step-by-step process that turns a complex physics problem into a clear set of safety checks. First, they identify every possible side force. Then, they calculate the bending moment, that's the twisting force those loads create. Next, they determine the critical load, which is the absolute max weight the jack can handle before it buckles. But the real magic happens in step 4. They take all of that info and use a safety formula to check that the combined forces are well within safe limits.
And it all boils down to this one simple, powerful idea. The combined forces must never exceed 100% of the jack's total strength. That's it. That's the core principle. And it's usually expressed in a special equation called an interaction formula.
Okay, don't let the letters scare you. This is actually a brilliant and simple idea. Think of the jack's total strength as a budget, like a strength budget of 100%. The first part of the formula calculates what percentage of that budget you're spending just to fight the vertical weight, the buckling risk. The second part calculates the percentage you're spending to fight off those side forces, the bending risk.
And the rule is simple and non-negotiable. The sum of those two risks must be less than or equal to 1. You cannot go over budget, ever.
So that math is obviously the foundation of everything. But designing for total safety, it's more than just math. These calculations are vital for sure, but they're only one piece of the puzzle. Real-world, dependable safety comes from a much bigger, more holistic approach that reinforces that engineering from every possible angle.
And here are the pillars of that total safety approach. You start with superior materials, using high-strength steel that has just the right amount of elasticity. Then, manufacturing precision. We're talking extremely tight tolerances. Of course, the system design itself is key. Properly installed guide rails to minimize those side forces. Even proper lubrication plays a role. And all of this is wrapped up in strict adherence to international safety codes. You see, each one of these is another layer of defense.
And that brings us to this number, greater than 1. This is the safety factor required by all those standards. So what does that really mean? The big takeaway here is that every modern hydraulic elevator is, by design, fundamentally over-engineered for safety. That safety factor means the jack is intentionally built to handle forces far, far greater than anything it will ever actually encounter in the real world. It's safety on top of safety.
And that really drives home this core idea. Safety isn't an accident. It's a calculation, a material choice, and a commitment to precision. As the analysis from the team at Novan Puyai Elevator makes clear, that silent battle happening inside the elevator shaft, it's won way, way before you ever step inside. It's won on the drawing board, on the factory floor, and during the final installation.
So, the next time you step into an elevator and press that button, maybe you'll think about that silent, powerful engineering holding you up. It's this quiet, incredible testament to human ingenuity, taking all this complex physics and turning it into something we rely on every single day without a second thought. That smooth, silent ride is a victory of engineering that's won for you over and over again. Thanks for joining this explainer.